Assalamualaikum, my name is Muhammad Mazik bin Muhammad. I'll be starting the video presentation for group 3. So for the industry that we choose for this group presentation is XY Electronics. So what is XY Electronics? It is a global industry pioneer specializing in sensor, magnetic and specialized electronic component. Its production context is managing complex, high mix, low volume assembly demands that require minimal downtime. It focuses on 24 sequence manual steps for component assembly, soldering, bonding and testing of products. So the problem statement, there is 3 problem statements for this. So the first one is cycle time mismatch. Severe line imbalance exists where individual workstation cycle time exceed customer demand space. The second one is critical constraint areas. The header assembly and complementarity and pre-testing 3 stations severe as primary bottleneck zones. And lastly, operational impact. Imbalances triggers localized inventory accumulation, high physical stress, and up to 60% idle time downstream.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amiruddin Bezukifli. My matric number is AD220070. Okay, so I will present of the literature review of our group project. So first is lean manufacturing. At its core, lean is about systematically eliminating model. There is waste in Japanese. We're talking about any activities that consume resource but delivers zero value to the customers. The classic 7 ways include overproduction, waiting, unnecessary transport, excess inventory, pointless motion, overprocessing, and defects. Our goal is to maximize value added work while driving down both cost and idle time. And then we move to the value stream mapping or VSM, originating from the Toyota production system. VSM is a visual diagnostic tool. It maps two parallel flows, the physical movement of material from a raw state to finished product, and the information flow, schedules, orders, forecasts. So what makes VSM powerful is its ability to highlight cycle times, waiting periods, inventory build-ups, and critically bottlenecks. It forces a clear distinction between what actually adds a value and what doesn't. And then the third one is takt time and line balancing. So takt time is essentially the heartbeat of a demand-driven production line. The formula is straightforward: available working time divided by customer demand. In our case study, that gave us 264 seconds per unit. Line balancing is the practice of distributing tasks across a workstation so that each one operates as close as possible to the talk time. When done properly, it can minimize idle time, slashes work in progress inventory, and prevents operator overload. It requires a careful task breakdown, rational operator allocation, and workload smoothing. And then finally is fishbone analysis, also known as the Ishikawa diagram. This is a root cause discovery tool shaped like a fish skeleton. So we use the 6M's framework: machine, materials, method, manpower, measurement, and environment. The value here is moving beyond surface symptoms, like slow cycle time, to actual root causes, such as equipment downtime, a poor layout, or insufficient training.
In this study, we used a descriptive quantitative case study approach. This approach was suitable because the project focuses on analyzing numerical production data from a real manufacturing process. The data involve cycle time, operator allocation, takt time, and workstation performance. The case study was conducted on the product A assembly line at XY Electronics. The scope of the methodology focused on the 24 sequential manufacturing processes involved in producing product A. So these processes include assembly, soldering, curing, inspection, and also testing activities. The first step in our methodology was to identify the current production process. We studied the overall production flow to understand how each workstation is connected from the first process until the final testing stage. So this helps us understand the actual condition of the production line before any analysis was carried out. So next, we collected the required production data. The main data collected was the actual cycle time for each process. So cycle time refers to the time taken to complete one unit at a specific workstation. We also identified the operator allocation or headcount provided at each workstation. This information was important because workstation performance depends not only on process time but also on the number of operators assigned. And after that, we applied a value stream mapping or VSM. VSM was used to visualize the movement of materials and information throughout the production line. By using VSM, we were able to present the current production flow in a structured way. This method also helped us observe delays, waiting time, work in progress areas, and possible non-value added activities. Then, we calculated the takt time. Takt time is the required production pace needed to meet customer demand. In this project, takt time was calculated by dividing the available working time by the total customer demand. This calculation gave us a standard time reference to evaluate whether the production process was operating according to the demand. Next, we perform line balancing analysis. In this step, the cycle time of each workstation was compared with the takt time. This comparison helped us evaluate whether each process was within the required production pace. We also calculated the cycle time per headcount by dividing the actual cycle time by the operator share provided. This allowed us to assess workload distribution across the production line. And finally, we use an Ishikawa diagram, also known as a fishbone diagram, as part of the root cause analysis method. This diagram was used to organize possible causes of production imbalance into several categories, such as machine, material, process, and management. And by using this method, the analysis became more systematic and easier to understand.
So let's move on to result and discussion. So the first one is current state and takt time calibration. So comprehensive time study of 24 manual semi-automated steps mapped across a single 11-hour shift. So the available production time is 11 hours times 360 seconds, which is equivalent to 39,600 seconds of net available time per day. So the customer demand per target is a fixed contract rate requiring 150 finished units product per shift. So the operational heartbeat is calculated take time of 264 seconds over 150 pieces. Any step exceeding this pace breaks the demand fulfillment. So let's move on to the second one, which is the root cause investigation or Ishikawa diagram. So the legacy automated sub-modules suffer from unoptimized cycle setting and requiring breakdown delays. The second one is process barriers, high physical handling times caused by complex manual adjustment, tight inspection loops, and slow manual clamping. The third one is management gaps, unbalanced operator allocation, and a historical lack of multi-skill cross-training across adjacent stations. And lastly, material variability, Minor dimensional variance in incoming raw frames require time-consuming hand alignment by operators. And lastly, it is the line imbalance and downstream impact. So underutilized stations such as core to header assembly at 46 seconds per HC run up to 5 times faster than bottlenecks. Work in progress buffer swelling. Bottleneck stations act as physical dams, causing substational work in progress stockpiles. Downstream idle time. Severe operation mismatches force downstream manual operators to remain idle for up to 60% of their shift. Operator stress. High pressure concentrated on a few manual bottleneck stations increase worker fatigue and potential defects.
Assalamualaikum warahmatullahi wabarakatuh, and good evening to everyone. My name is Muhammad Isham Muhammad Rijal, and my matrix number is CD220003. I will be explaining for the conclusion of this presentation. First, what we did discover is that the production line for product A at XY Electronics is seriously unbalanced. Out of 24 process, 6 exceed the takt time of 264 seconds. But out of two stations, stand out as the worst bottlenecks. The header assemblies and complementarity takes 524 seconds, almost doubled at the limit, and pre-testing 3 at 325 seconds. These are the choking the entire line. So why this happening? Using the fishbone analysis, we entraced the root cause at to four areas. First, the machine inefficiencies, like slow cycle time, complex manual process that takes a long time, takes too long. There's the management gaps, like uneven task distribution and even material inconsistencies that slow down the assemblies. That we propose, Now what we propose is that three practical solutions. One, reallocate the operators. Some stations are severely unutilized. For example, step 2 and step 11 have fractured operators, and we can we can combine those resources and move them to the support support the bottleneck station. Two, the introduce of cross training. This gives us the flexibilities. Operator from quieter station can step in during peak demands um, without overworking any single persons. Third, the simple physical movement. Add a quick release pneumatic clamp to reduce manual handling time, and put up the visual management board so everyone can see line stoppage immediately. And for the final outcome for this is the um, with the change, the line can realistically meet the daily demand of unit 150 unit without hiring new people. More importantly, this approach balance speed with fairness. We're not just pushing operator to work faster, we also redesign the work itself. So the our key message in this is that true lean manufacturer isn't about rushing, it's about eliminating imbalance through smart task design and sharing resource. Thank you.